Hello everyone. Hello everyone. Ah, on this video, we are going to talk about the energy conservation. Okay, and energy conservation at the very beginning, in energy conservation, I believe in every textbook mention about one terminology called conservative force. So at the beginning, we'll just do a very short introduction of the conservative force. Yeah, what's conservative force and what is non-conservative force. And conservative force, yeah, it's very hard to explain. Okay, let's see what most textbooks say. It said for conservative force, the work done in moving between 2 points is independent of path taken. Simply speaking, it said the work done by a conservative force is path independent. Okay, and another description is for conservative force is the work done by conservative force is path independent, and the work done in going around any closed path is zero. Okay, so that's the description of a conservative force. Yeah, it sounds very academic, but we will use a very simple example to demonstrate this point and show that really a conservative force is really the work done by conservative force is really a path independent. Okay, okay, so we will use first of all, we use the spring force, okay, and then we'll use the gravitational force. And spring force and gravitational force, these two forces are really special because they are all conservative force. And the next semester, we are going to talk about electric field. Electric force is also a conservative force. I think electric force is also conservative force. Yeah, electric force is also conservative force. Okay, but we'll talk about electric force next semester. And this semester was just talking about potential elastic force or spring force and gravitational force. Okay, so and let me start with a very simple example. Suppose we have we have a spring. Okay, and we pull a spring, and we take a two paths. Okay, okay, we pull the spring, and initially this spring is unstretched. So that means this spring is at its equilibrium position. And unstretched, and we pull the spring, and we goes to path one. First of all, path one is I stretch the spring from 0 to 4, and then pull, and then gradually back to 2. Okay, and the path two is just pulling the spring from 0 to 2. And I will try to calculate the work done by the spring force in path one and path two. And you've noticed the point, the path one and path two, their initial position and final position are the same. The initial position is O0 and final position is O2. Okay, they are O2. Okay, but the difference is these are two different paths. Okay. Okay. I think if I'm clever enough, you already see the answers. Okay, they are pretty much the same. So the spring force is really a conservative force, but we still just pretend we don't understand anything. Just pretend we don't understand. Okay. Okay, and I pull the spring as constant velocity. Pull the spring at constant velocity, and at a constant velocity, a constant velocity. Okay, and why should I pull the spring at a constant velocity? Because if I don't pull the spring at a constant velocity, there will be a kinetic energy issue. Okay, simply speaking, I just write a very simple way. If no constant for constant velocity, if no constant velocity, we will have kinetic energy issue. Okay, but right now I don't want the kinetic energy involved. We will have a kinetic energy issue. Kinetic energy issue. hmm Because work kinetic energy uh, because work kinetic energy theory tell you. Yeah, if you are applying a constant velocity, your velocity changes. Okay, that means the kinetic energy changes. Okay, so we have the kinetic. You have to consider the kinetic energy as well. If the velocity change, you have to consider kinetic energy. But right now we don't want to involve any kinetic energy. Okay, so that's just why we have to put a constant velocity. And okay, let me write down. Okay, the F spring is here. Okay, at the constant velocity, F pull equal to F spring. Okay, and by Hooke's law, because it's a spring, so it's Hooke's law. F equal to F spring equal to F spring equal to minus kx. K is a force constant. And the K, what value we should use? Okay, let's just say our K is 5 newtons per meter. Okay, and the length, the unit of this distance or x coordinate is yeah, let's just say it's a meter. Okay, MKA system, like MKA system. Okay, so let's calculate the work in the path A. Okay, work path A. Oh, no, pass one. Actually, pass one has two sections, so we can separate these two sections, 0 to 4, and plus the work done by the spring force. Yeah, one to calculate the work done by the spring force, and the other section is 4 goes to 2. Yeah, okay. Okay, so and the spring force is a varying force. It's a varying force. It's a varying force. Okay, varying force. Okay, if we want to calculate the work done by a varying force, what should we do? We have to use integration. Okay, 0 to 4 m minus because f spring dx plus 4 to 2 f spring dx. Okay, because it's varying force, well, so we have to use the integration to calculate the work done by varying force. And okay, so the k is equal to 5, so let's put in everything 5x dx plus 4 to 2 minus 5x dx. And this very simple power law, but not power function integration. So I hope, yeah, I believe you're in, I believe your calculus class has already done this. So it's minus 5 is the constant factored out, and it's equal to 1 over x squared 0, 4. Then plus minus 5, okay, factoring out, and 1 over 2. 1 over 2 x squared, and it's 4 to 2. Okay, so I think we are almost close. So this is minus 5 is 1 over 16 minus 1 over 0. And plus minus 5 is 1 over 2 is 2 square minus 2, 4 square. Okay, so this is 8. So it's minus 14 plus, and this is, what value it is? 2, 4. 2 squared is 1 minus, it's 8. 1 minus 8, is this correct? Is this correct? One minus 8, so it's 35. Okay, overall it's minus 5. Okay, from this result, we see on the first section is positive, second section is, sorry, the first section is negative. 0 to 4, this section is negative. Sorry, that means this section, spring force, is negative work, is doing negative work. Negative work. And for 4 to 2, it's doing a positive work. Positive work. This is a feature of conservative force. It can do the positive work and negative work. And at the end of this section, we will introduce another non-conservative force called friction. Friction is only negative. Okay, friction never has positive. Okay, so that's a feature of this conservative force. They are negative and positive, and we will demonstrate more example about this. Okay, so the pass one, the total work is -5. Okay, what's about pass two? Pass two is just pulling the spring from 0 to 2. Okay, pass two. Let me say pass two. Pass two. Pass two work. Pass two. Okay, it just pulling the spring from the equilibrium position to the +2. So it becomes very reinforced. We also have to use integration. Okay, sorry, the range is wrong. Have to use integration to doing the work calculation. Okay, 0 2 and minus kx dx. And k, we say k is 5. So, okay, so k is 5. So the same thing is -5 is 1 over x squared, 0 2. So what the answer will be? What the answer will be? Okay, -5 on the 2 squared minus 0 squared. Okay, so answer is -5. Mm-hmm. The unit is joule. Okay, in MKS system, unit is joule. Oh, so you see in the past one, from the past two, past one and past two, they both had the same work, 5 -5 joule. And you see, like I say, the past one, the initial position is 0, in final position is 2. Okay, initial position is 0, final position is 2. And past two, initial position is 0. Okay, final position is 2. Okay, so these two different paths, but they have the same initial position and final position. And finally, their work, we calculate the work on these two paths. It's really path independent. Okay, okay, work. Okay, W path 1 is equal to path 2. So that's a very simple proof. Okay, but maybe it's not very comprehensive proof, but it's tell you, okay, the work, the spring force, work done by force. Okay, work done by spring force, work done, okay, work done by a spring force. Spring force is done by spring force only take care only takes care about uh, the initial and final position. Initial and final position. Okay, that's a feature of conservative force. The work done by conservative force, it only take care about its initial position and final position. And spring force, this simple calculation tell you, yeah, it's really independent to pass. You only take care about your initial position and final position. And once your initial position and final position are same, but initial position are same, so they will have the same work. Okay, this what this graph shows. Okay, what this sentence mean for conservative force? The work done in moving between 2 points independent of the path. Independent of the path taken, it only care about initial and final points. Okay, that's called path independent. Okay, since in a closed path, the initial position and final position is the same. That's called closed path. Okay, since the initial position and final position are the same in any closed path, then so that means the work done by conservative force done in going ground is the work done by conservative force in any closed path is zero. Okay, because it's only take care about its initial and final position. Okay, and that's for proof for the spring force. Okay, I hope you can familiar with this idea. Okay, and next example will show you the gravitational force. Okay, gravitational force has the same feature. It's also independent to pass. Independent to pass. It only also take care about your initial position and final position. Okay, we'll see in the next example. Bye bye. Okay, hope you understand this. Just stop here. Okay, the same. Oh, okay. See you. Bye bye. Now I'll prepare to close here.